Okay, good. I think we are live. And hi, everyone. Today is our day two for Canadian Computational Neuroscience Symposium. And today in the morning session, we have neuromodulation, and in the afternoon, we have computational psychiatry. And we start with Andrea and I will start our introduction. I'm going to share my slides first, and then I'll pass it to Andrea to go through computational psychiatry. Into my slide. Focus. And okay, perfect. Just to start, I wanted to give you this clarification for neuromodulation devices versus neuromodulatory systems that Andrea will talk about. For neuromodulation system, well, we have it's actually technology that deliver electrical or pharmaceutical agents directly to specific area, for instance, in the brain. And neuromodulatory systems is different in the brain, provide foundation for cognitive functions. And just example for neuromodulation devices, we have a lot of devices. And so just one example is deep brain stimulation, and the other example is transcranial magnetic stimulation. And by this slide, I want to just emphasize on different levels of stimulation and different level of observation that we can have with different neuromodulation devices. For instance, with deep brain stimulation, the stimulation can be very local in single neurons, and in transcranial magnetic stimulation, or TMS, it can be very wide. The application of closed loop neurostimulation, I'll go back to this closed loop in 2 slides, is ever increasing. It's ranging from medical, clinical application to education, sports, and entertainment. One good example of the successful outcome of neurostimulation device, specifically the one that I provided here, I meant by deep brain stimulation, was in the treatment of movement-related neurological disorders like Parkinson's disease, dystonia, and essential tremors, where neurosurgeons can insert these electrodes very deep in the brain, and depending on the type of neurological disorders, they can put it either in a basal ganglia network, for instance, SDN or GPI, or in the thalamus, and deliver high-frequency pulses to reduce symptoms associated with these neurological disorders. I wanted to use this slide where on the right you can see kind of a neuronal circuit underlying basal ganglia network. As you can see here, we have a striatum. Here it is the substantia nigra part compacta that provide these dopaminergic neurons. And we have GP, STN, subthalamic nucleus, and then it goes all the signals in either direct or indirect pathway goes to, plus hyperdirect pathway, go to the thalamus, and then from there to the cortex. Now, the point with this slide that I said it's kind of motivational for me is that as computational neuroscientists, we can create this. We can create. Yep.
Sorry. Could you press hide for the small?
Okay. Yeah.
Yeah. Window. Perfect.
Yeah. And yeah, as I said, it's motivational because we as computational neuroscientists, we can create different parts of these neuronal circuits. We can create single neurons, we can create synapses, and then go through the whole circuit. But the point is, When I look into the whole idea of neuromodulation and closed loop neurostimulation, is that we use computational neuroscience to do what? We want to have some understanding about the mechanism underlying specific circuit in the brain. So if we assume that this circuit is, for instance, basal ganglia network, then the whole point of computational neuroscience is, well, it's not the whole point, but part of that is to understand the mechanism. And if we understand the mechanism, we can have better understanding how this goes wrong in neurological disorders. And this is super important because we can provide with the model, with some insight from the model, we can provide some prediction for neuromodulation to have a better, let's say, stimulation, to locate in a better position or area in the brain, to have optimal type of pulses or frequencies to do restoration. Okay, what we want to restore for sure is the normal brain activity or brain function in the brain. But the reason I'm saying this link between computational neuroscience and neuromodulation is that we don't do this modeling just because it is cool or just because we have a good model. We do this because we can see the application. We can see that if we have a good model, if we can do a good job and have a better understanding of the mechanism, we can provide this insight for neurosurgeons. And this is useful because this will be used to treat, for the treatment of patients with neurological disorders. So this is probably, this can be interesting for who want to pursue in the field of computational neuroscience, which can feel the application and how useful is these computational models for patients. My last slide before I pass to the slide to Andrea is I talk about the computational neuroscience and understanding mechanism, but the need for multi-scale brain modeling is something that mostly from my side, it's coming from my background in engineering. And the point here is that we have a simulation. We can stimulate different regions of the brain. And for instance, with deep brain stimulation, we can do so in basal ganglia network or thalamus. When we also have recently the application for other areas in the brain. But the point is, the way I look into this problem is that we can have a stimulation or intervention in the brain while we can have observation in different scales. It can be neurons, single unit recordings where we have access to the spikes. It can be local field potential, which is kind of the average of several neurons, and we can have ECOG or EEG. So we can have observation in different scales. And with the modeling, the point is that we want to build these models to have a better understanding. But with neuromodulation and the need for multi-scale brain modeling, the point is how to use this simulation, because we can use the whole, different regions or different substructure of the brain as a black box for which we can have some biophysically motivated models. But the way that we can look into neuromodulation is that we can provide the input to this system and have access to the output. So given input-output relationship with some let's say biophysically motivated, biophysically realistic models will help to do this for sure better understanding of the mechanism, inferring the mechanism, and do this multi-scale brain modeling. Okay, with this introduction, I'm going to stop sharing my screen and pass this slide to, okay, so Andrea, these are your slides, yes? Okay.
Perfect.
Focus on the screen and go ahead.
Okay, so I will take it over. Okay, perfect. Can everyone see my screen okay? Great, so I will talk about neuromodulation in terms of chemical neuromodulation that supports plasticity in the brain. And I'm particularly focusing on my tutorial on the neuromodulatory systems, as this is particularly important for psychiatry and using model-based approaches to predict treatment response. Okay, 1 second. For example, in schizophrenia, the dopaminergic and the cholinergic neuromodulatory systems. So we see here the dopaminergic system on the left and the cholinergic system on the right are particularly important for, in the context of schizophrenia, for us to be able to use a model-based approach to predict treatment response to typical antipsychotic medication, for example, but also atypical medication that has additional cholinergic functions. In the context of affective disorders, we are particularly interested in understanding the interactions between the serotonergic system that is displayed here on the left, as well as the noradrenergic system that is displayed on the right. How can we use mathematics to understand these complex interactions between neuromodulatory systems? Well, first, I want to take a step back and try to emphasize that a unified mathematical formalism can be particularly important in this context. Mathematical formalisms in physics have provided immense progress as they were able to link seemingly unrelated observations and helped us generate new hypotheses. An example of that are the Maxwell equations of electromagnetism. Of course, I won't go into the Maxwell's equations in this talk, but rather start by posing the question, can we describe the function of the neuromodulatory systems using a set of mathematical equations? The intuition behind this mathematical equation that might be useful for us to understand the complex interactions of these neuromodulatory systems is related to a framework that aims to integrate Bayesian models of perception with Bayesian models of cortical computation. And the intuition behind this is the idea that the function of the brain is to make predictions about states in the world. So we have this mapping between the inferred hidden states that are represented in the brain and the true hidden states that are out there in the world that we don't really have access to. Our percepts allow us to process incoming sensory data, and in this Bayesian brain hypothesis, the sensory data is translated into the brain as prediction error signals. Prediction errors that reflect the discrepancy between our model of what caused those states in the world and the inputs that we receive from the world, the evidence that we obtain through our senses. This continuous process of adjusting the model is what one might formalize as the function of the brain. In other words, we could posit that the brain is an inference machine, and we conceptualize beliefs in terms of probability distributions that are updated via the Bayes rule that proposes that predictions are a function of prior beliefs under a governing model of the world, the sensory data that we obtain from the world normalized by the evidence. Now, if we take this approach in a hierarchical fashion, as proposed by my colleague Christoph Matthijs in the hierarchical Gaussian filter, we can approximate these hierarchical Bayesian formulations and obtain updates that take the form of precision-weighted prediction errors. According to this generic formulation of Bayesian inference, the belief update, the degree to which we update our model of the world is proportional not only to a prediction error, this discrepancy, this difference between our model and the sensory data that we obtain, but also a ratio of precisions that determine the impact that prediction errors have on belief updates. So in the numerator, we have the sensory precision, which amplifies the impact that prediction errors have on the belief updating process. But on the other hand, on the denominator, we have the belief precision that reflects our top-down confidence in our model of the world, and that dampens the impact that the prediction errors have on our beliefs. In other words, the sensory precision of the prediction error reflects what we are learning now, whereas the belief precision reflects what we already know. So this is an example of a graphical representation of this generic model that proposes that events in the world are caused by a state that governs the association strength that determines how frequently these events occur. And that association strength is determined by the volatility or the context in which that association strength is deemed to be true. So an example is here below. This reflects, in red, is the belief update that an agent has about an event that occurs with 50% probability, essentially at chance. So you see that the belief update hovers around this 50% mark. Now we have a change in the environmental context when things become very predictable. Even when we present the same input structure, now the belief update, the size of that belief update is much larger because the agent is expecting there to be an additional change in environmental context. So this reflects learning, the learning rate as a dynamic process. So the degree to which we take prediction errors into account depends on how volatile the association strength is perceived to be. So if we express that ratio as a variable psi, we can take these two variables that are actually states because they change dynamically from trial to trial, from new exposure to sensory inputs. We can take these states and we can formalize them in a general linear model fashion. So this is the idea behind models of neuromodulation. We want to explain changes in brain activity, or if we take functional magnetic resonance imaging, for example, changes in voxel time series as a function of these computational quantities, such as, for instance, precision-weighted prediction errors. We express these in our general linear model, and then we look at what parts of the brain change as a function of these quantities. Now, this demonstration was done in a study conducted by former colleagues of mine in Zurich, in Switzerland, at the Translation and Neuromodeling Unit, led by Dr. Klaas Stephan, using a task that was a simple associative learning task where an auditory cue was paired with a face or a house. The association strength of those two cues change in time with this probability structure. The figure in red, the time series in red, reflects the belief update of an optimal Bayesian agent. Now, we can extract, based on subjects' performance and fitting the model to subjects' behavior, we can extract these precision-weighted prediction error quantities. And interestingly, what my colleagues found was that the lower level precision-weighted prediction error that updated beliefs about outcomes was represented in the dopaminergic midbrain, whereas the prediction error that updated beliefs about the volatility of those association strengths was represented in the cholinergic basal forebrain. While I was working in the translation neuromodeling unit group, I also did an experiment now asking agents to make associations about socially relevant quantities such as advisor fidelity, which also changed in time. We used a similar modeling framework, and we were able to reproduce this dissociation between lower level precision weighted prediction errors that updated beliefs about associations in the dopaminergic midbrain and higher level precision weighted prediction errors that updated beliefs about the volatility of intentions in the cholinergic basal forebrain. Now, the model allows us to estimate for each individual a series of quantities that range from prediction errors to precisions stacked at higher and higher levels in this processing hierarchy. We can take these equations and we can take these quantities, these predictions and precisions, and look at their representation in the brain. Previous studies have used similar models, particularly reinforcement learning models, and have associated these quantities, the prediction errors and the inverse of precision, which is uncertainty, to specific regions in the brainstem, such as the dopaminergic midbrain for reward prediction errors, the sensory precision in the same region, expected uncertainty in the basal forebrain, and unexpected uncertainty in the cholinergic locus coeruleus. So what if we can place a mathematical equation for each of these neuromodulatory systems and very precisely investigate their functions and their interactions? So for example, low-level prediction errors and precisions as related to the dopaminergic system, higher-level prediction errors related to the cholinergic system, valence prediction errors and precisions for the serotonergic system, and higher-level volatility precision for the noradrenergic system. And this will become more evident when we discuss the context of this model-based approach in psychiatry, and in particular in schizoaffective disorders. So I'd just like to end by thanking my collaborators from Toronto, Switzerland, Zurich and Basel, and other places in Europe. And thank you for your attention.
Great. Thank you, Andrea. I'm going to unfocus the screen and see the questions. Okay, we have one question to start answering. Do you see the question, Andrea?
Yeah.
Okay, so start answering. Yeah.
So the question is,
yeah, go ahead.
Did you get reliable results for clinical use from modeling? What is your prediction for the near future? So, of course, we are investigating the robustness of these parameter estimates so that we could use them for making clinical predictions. And this is a very important component, and it depends on two things. It depends on the task that you use. So how do you study that clinical question? In which context do you study it? It has to be probed in a very specific fashion. So for example, if you want to study persecutory ideation in psychosis, you want to probe it with a task that taps into how people learn about intentions, for example. And then you have to design the experiment with a model in mind. You have to, before you even acquire the data, you have to ensure that the parameters are recoverable if you simulate data and then estimate the simulated and estimate the parameters based on the simulated data to ensure that you can recover the values that were used to simulate that data. And if you do those things, then the reliability is quite good. And for certain experiments, the effect sizes are moderate. So you can use these model-based approaches to address clinical questions. Okay.
You can go to this second question, Andrea. I start answering, and then you can read the question and then answer.
Mm-hmm. Is there a way to translate something like prediction errors into quantities of neurotransmitters, etc., in the system? So how do you translate that? So there's been a lot of there's been theories of cortical computation. So Dimitris discussed this yesterday about how prediction errors are passed on through to cortex. So the role of superficial layers, for example. I think in order to relate that to specific quantities of neurotransmitters, one must incorporate theories of cortical computation, such as the predictive coding. But one can propose something very specific, a very specific sort of cognitive network, and which connections are meant to propagate prediction errors, what aspect of the model reflects a function of precision, and can test that empirically.
Thank you. Any more questions? We have 2-3 minutes before the next session. If there's no further question, we can end the broadcast here and prepare for the next session. And we will be with you in a few seconds. Okay. Thank you, Andrea. Oh,
thank you.
Quick question from Francis. Yeah.
Maybe you can bring Francis.
Yeah, Francis, do you want me to bring you on the screen or? Okay, she posted. Can you say something more about, okay, so let me start answering. Can you say something more about different scales? Yes, different scales in my mind is that, so if I start from computational models, we have single neurons, and for sure we have also multiple levels, but I'm talking about cellular level. We have single neurons, we have a neuronal network, which is a combination of multiple neurons, and then it goes to, higher or larger networks, and then it goes to the whole brain model. And different scales, I mean that when we have observation corresponding to each level of neuronal representation. For instance, if you're talking about single neurons, we know that membrane potential is one level of observation. And if you give me membrane potential, I'll say that, okay, that's fine for single neuron models. And if you go higher, in a little bit higher level, where we have the spikes from some neurons, some neighboring neurons, or go a little bit higher where we have local field potential, these are the scales which correspond to different level of observation in a neural system. So this is what I meant by different scale. Okay, I hope that I answered the question. Okay, thank you everyone. We are going to end the broadcast here, and we'll be with you